So in this video, we will talk about supervised segmentation for classification. Now, as part of application of supervised segmentation, we will introduce decision trees, which are very easy to interpret and understand and have been very popular today for predictive analytics. Later on, we will see how we can expand the idea of decision tree to build bagged and boosted trees, including the random forest algorithm. So here is a very simplistic data set of a bank's loan write-off information. Now we have the customer attributes X, which is name, balance, age, and employed. We also have the response variable Y, which is yes, no. And this is the label or the class variable. So Y is a class because it's a classification problem. Now recall that if Y was continuous, then it would have been a regression problem. All right. So a particular row is highlighted, and here we call this as an example or an instance, right? And it's also called as the feature vector because a row is a vector of feature values. Okay. So the heart of today's topic is supervised segmentation, right? So what is supervised segmentation? Now there are two words. One is segmentation and the other is supervised. So segmentation refers to dividing the data set on a feature with some rule. Okay. By using a rule on a particular feature, we will divide the data set into groups. That's what segmentation refers to. And supervised refers to the fact that in the process of coming up with a division rule, we will actually use the Y variable. Okay. So that's what supervised segmentation means. So for example, in this data set, our variable of interest is whether the customer will default or not. That's our Y variable, and that's what we want to actually predict. So looking at this write-off information, I can divide the data into two groups such that one group has low probability of default and the other has high probability of default. So for example, we can say that if balance is less than equal to $10,000, then the default probability is 0.5. And if balance is greater than $10,000, then default probability is 0.05. Okay. Now these two are very different segments, as you can tell from the default likelihood. One is 0.5, the other one is 0.05. They are very, very different. So in this process, what I have done is I have used a feature, and that feature is balance. Okay. In supervised segmentation, we use one feature at a time to divide the dataset into multiple groups. So in this one segmentation scheme, I've used this feature balance. I could have chosen age or employed. So that's the feature. We have chosen balance, and the rule is less than equal to 10,000 and greater than 10,000. Okay. How did I come up with that rule? Well, the Y information, okay, the write-off information or the class information will be used to efficiently come up with that rule. We will see how to do that. All right. So I hope these things are clear. One is the feature that based on which we divide the groups, and there is a rule that gets applied to that feature based on which we divide the data set into groups. And how do we devise the rule? By using the Y information. Okay. And yeah, so one more thing, how did we select this feature balance? Why not age, or why not employed? Well, the supervised segmentation algorithm that we will use, for example, decision tree, that actually tells us which features are important or informative. Okay. So balance, in this example, balance is an informative attribute that helps us to create groups which have very different characteristics. All right. So we'll call balance as an informative attribute. Supervised segmentation process helps us identify informative attributes, and then split the dataset into groups which have very distinct characteristics. The important or informative features that we split on, we are able to easily discriminate between the segments. Okay. Now, the decision tree algorithm that we are going to look at is a form of tree-based induction. Okay, because we use trees to induce the idea of which feature are informative from a classification standpoint. Okay. One key note here: there is a subtle difference between predictive model versus a descriptive model. All right. In case of predictive model, we want to predict or have the best estimate for an unknown value of the target. In other words, given a set of features X, right, what is the best prediction of Y? And the performance of the predictive model will be based on how accurately it predicts Y compared to the actual value. Okay, so that's predictive analytics. In contrast, in case of a descriptive model, we don't want to predict any unknown target. Rather, we want to study and gain insights on features that constitute a particular class. Okay, so for example, in this default data set, we can isolate the instances which defaulted and study the descriptive statistics of those customers. Okay, what's their average age? What's the employment status? Okay, so we can segregate this data into two populations, defaulting and non-defaulting, and we'll study the descriptive statistics of these two groups. Okay, this is to better understand what constitutes a default behavior. Okay, what's the characteristics of the default population? The task is not given a particular customer, tell me whether he will default or not. That's predictive analytics or predictive model. Descriptive model tells you or describes the characteristics associated with a particular class. Okay, and we do descriptive and descriptive model to understand the population or the group better, and consequently it might lead to another model which describes why customer defaulted. Okay, so you create the group, create the group for the defaulting versus non-defaulting, study the characteristics of the group, and then based on the study you gain more insights to come up with another model which will describe the path to default. Okay, what are the sequence of events that lead to default, things like that. So that's the basic difference between predictive model versus descriptive model. To summarize, in predictive model we definitely have this kind of a problem where we are given an X, predict Y. Okay, in descriptive model we are just describing the behavior or the characteristics of a particular group by analyzing the features of that group. Before we proceed, there is one more distinction that we have to make. What's the difference between induction versus deduction? All right. In machine learning, induction refers to postulating a model to describe the general behavior of data from a set of specific examples. What's the starting point of a machine learning problem? You have a sample with you, and then you postulate a model for the population. So from the sample you derive insights about the population phenomenon. You actually use the sample, which is set up specific examples, and make general statements. Okay, in a way we are inducing a general framework from specific examples. This is called as induction. Okay, and it refers to the part where we select models from the data and assume that the model is generally applicable for the task. Okay, so that's induction. In contrast to induction, deduction means opposite. Deduction means given a set of general rules or even specific rules, you deduce other specific rules. For example, if you choose to use logistic regression to predict if a customer will default or not, that is inductive learning. Okay, because from the specific examples that we have in the data, we are learning a general function, logistic function that we are going to use across. Okay, and that function that we learn is the logit model. Okay, so learning a model from a set of specific examples is an example of induction. This is called as inductive learning. Okay, looking at specific examples, we come up with general statements or general functions that we learn, which we hypothesize that the entire population is abided by that rule. Okay, so that's induction. Now then, so what will be deduction? Deduction would be using this model. Okay, we predict a particular customer will default or not. That's deduction. So going from specifics to general is induction, and going from general to specifics is deduction. Okay, back to the core topic of discussion. So let's say we have a customer default dataset. Now we have two categorical features, married and employment status. Married has two levels, yes or no. Employment status also has two levels, business or salaried. And our target variable, which we want to predict, is default, and it's binary, yes or no. Okay. Our training data consists of 8 customers or 8 examples or 8 instances, you can say. And our goal is to develop supervised segments to be able to predict if a test instance will default or not. That's our goal. So using this training data, we will create supervised segmentation, and with the help of those segments, we can actually predict if a test instance, that means a customer which is not part of our training data, will default or not. Okay, so that's our goal. Okay, before we explore the algorithms, if I ask you what is the most naive estimate of probability of default for this particular test example? Okay, so probably the most simplistic raw estimate of probability of default is the one that does not even take the x or the features into account. We can actually give an estimate by just looking at y. All right, it will be very raw and very simplistic or crude estimate, but that's the most basic estimate you can produce. Okay, just by looking at y, we can say that okay, there are 8 examples or 8 customers. Out of those, 4 defaulted, irrespective of their features. 4 defaulted out of 8, so the probability is 0.5. Okay, this is probably the least expensive way of coming up with an estimate, and it completely ignores the features, right? And we can actually call it as unconditional PD, because the moment you provide features, feature values of a particular customer, and you predict based on the features, it becomes a conditional PD, right? Probability of default given X. Here in this example, we did not even use X. So you can call it as an unconditional PD, and that could be a starting point of your analysis. All right. Okay, but we have features, right? So let's use them. But which features to use? Which features to segment on? That's the question. How do we choose informative attribute? That's what we are trying to find out. So here we have two choices. We can use the feature married, or you can use the feature employment status. Okay, which feature is better or more informative? Let's find out. Now, if we choose to use the feature married, then we can segment our customers like this. The feature married has 2 values, so we can segment in only one way: married equal to yes or married equal to no. Okay, so to begin with, we have 8 customers, right? 1, 2, 3, 4 up to 8. Call this segment as node 0. Okay, we also call this as root node. Call this N0. Okay, as that stands for root node. Then we split the data set into 2 segments, one with married equal to yes, the other one is with married equal to no. And as I said, this is the only way in which you can split, because married is a categorical variable. To be specific, it's a binary variable. There are only 2 values, so there is only one way you can split. Using married, you can split the data set in only one way. Now, if we look at the split, the customer 1, 2, 5, and 7 belong to the first segment, and customer 3, 4, 6, 8 belong to the second segment. Call these segments as N1, N2, just for convenience. Now that we have branched, right, let's calculate the probability of default in both these segments. What is the probability of default in node 1? Well, it's simple. Out of 4, only 2 defaulted, right? So there are 4 customers, 1, 2, 5, and 7. If you look at the original data, 1 and 5 are the customers who defaulted, right? So 2 out of 4 defaulted. So that means the conditional PD, we can call this as conditional PD, because probability of y equal to 1 given that the customer belongs to node 1. So it's sort of a conditional PD. Now that we have branched, we have added conditions. Okay, depending on depending on which group a customer belongs, his PD will be different. Okay. All right, so in node 1, the probability of default is 1 by 2. How did I get that? Because 2 out of 4 customers defaulted in node 1. Any customer which falls in this node 1, my estimate of probability of default for that customer would be 1 by 2. Okay. Similarly, in the other node N2, again, there are 4 customers and only 2 defaulted. So 3 and 6 defaulted. So in node 2 also, my probability of default estimate is 0.5. Okay, this is pretty straightforward. Now let's try to split based on the feature employment status. The steps are exactly similar. So here, feel free to pause and work it out. Okay. So if we go by employment status, again, that's a binary variable, so there is only one way you can split the data set. If we look at N1, the probability of default is actually 1, because in node 1, all the customers have defaulted. So it's 4 out of 4. Going by frequentist approach or by proportions, it's 4 by 4, that's 1. Okay. Similarly, if you look at node 2, none of the customers defaulted. So my probability of default, if given that customer belongs to node 2, is 0. Okay. Now this is a toy data set, which is just for illustration of the key ideas. So don't get alarmed with the extreme probability values 0 and 1. In practice, we will not have this kind of scenario. Okay, let's compare the 2 splitting schemes. Okay, in the first example, we split on the feature married, and in the second example, we split on the feature employment status. Now let's compare these 2 splitting schemes. So which splitting scheme do you think worked better? In other words, which attribute you think was more informative? The answer is employment status. Now, without any feature, the blunt prediction was half and half, right? That's what we started with, right? So when we came up with our naive prediction, it was that probability of default is half, and that did not involve any feature at all. Okay, now when we are trying to use features, what we want is the probabilities to be skewed away from half and half. In other words, we want segments which are pure or homogeneous. What does that mean? It means that we want segments which are either heavy on defaults or heavy on non-defaults. What we don't want is a uniform mix of defaults and no defaults, which is exactly what we had in node 0. That was a completely impure set. When you are when a customer is in a set which is completely impure, it means there is, let's say, 50% representation from one class and 50% representation from the other class. Then the customer in that group is having an identity crisis. Where does it belong? Okay, in a group where there is uniform representation from both classes, my prediction will be inaccurate. Okay, if I get a purer subset, for example, think that there is a group where 90 out of 100 people have defaulted. Any customer who belongs to that group, I can say the probability of default is 90%. Okay, so that's why I always strive for purer and purer subsets, subsets which are homogeneous, subsets which are purer in one particular direction. What does that mean? That means I want subsets which have an overwhelming representation of one particular class. Okay, other classes should be minority in that group. Only then I can be confident in my prediction. Okay, so in this example, what happened? In this example, when we split on married, it did not make the segments purer. Initially, I had a 50-50 representation. My probability of default was 1/2. After splitting on married, I ended up with two subsets, but the PDs did not improve. I still have a uniform mix in both these subsets. Okay, so splitting on married really did not improve my prediction. It did not add any value. That means married is a non-informative attribute. Okay, but in the other scheme, when we split on employment status, we got two completely pure segments. Okay, we got node 1, which is essentially the defaulting segment, and node 2, which is the non-defaulting segment. Any customer who belongs to either of the groups, you can clearly tell what kind of a customer he is. Whatever is your estimate of PD on either of these groups is more accurate. All right. Let me rephrase that. Your prediction of y equal to 1 or 0 will be more accurate because the groups are homogeneous. Okay, the groups are either purely in 0 direction or 1 direction. So depending on that, your prediction will improve. Prediction of y. Okay. All right. So what we discussed is that with segmentation, we desire to gain impurity, or you can say we want to reduce impurity. All right. Now you can guess that obviously to create efficient branching and to create identify informative attributes that result in maximum impurity reduction. Okay, first we need to define impurity and measure impurity mathematically. Once we measure the impurity of a group mathematically, then we can find out which feature at what value I need to split so that the resulting impurity of the children, that means the subsets, is much less than the parent. That's the whole idea. Okay, so how to measure impurity mathematically, we'll see that shortly. Before that, one thing though, for sure we want that in every split our subsets should be purer and purer or more homogeneous. Okay, But in practice, we actually don't want 100% purity in any segment. As in this case, this example, this is a toy example. This is just for illustration. But in practice, we want to avoid 100% purity. Can you think of why? Pause the video and try to come up with an answer. Okay, the answer is one word: overfitting. We don't want to overfit. Meaning, as per our example, we should not create a rule that anyone who has employment status equal to business will default with 100% probability. That is what the second example tells us, right? So if you see here, whoever has employment status as business, we are saying you will default with 100% probability. So when you have purer, I mean completely pure subsets or subsets which have 100% purity, your probability figures will go to 1 or 0 depending on what we are trying to say, and that practically makes no sense. Okay, so we do want to retain some level of impurity just to avoid overfitting. Okay, so we'll see that later. All right, now before we come up with an algorithm and a measure of impurity, we want to understand the various challenges that we have. So first of all, some of the features could be binary, but some could have multiple attributes. For example, in our previous example, we had the variable employment status, which had 2 levels: business or salaried. Now imagine the same variable, employment status, it could have 3 levels. For example, business, salaried, and unemployed. So if a feature has 3 levels, then when you split on that feature, it will be a 3-way split. Okay, actually there are algorithms which only do 2-way split even on features which have 3 levels. How can you do that? It could be like this. So employment status, I can split like this: business, not business. Then within not business, again it will come as salaried, not salaried. So there are ways to only ensure that I have 2-way splits, but you can do multiple splits. I mean, if there are more than 2 levels, we can exhaust that particular feature in that that splitting that we can do. But the challenge here is, there is a feature which is binary, so we'll do a 2-way split, and there is another feature which has 3 levels, so we'll do a 3-way split. Now, how do we actually compare which split is better? Okay, in case of if we are comparing 2 features, which feature to split on, or which is the more informative feature, but the challenge is with one feature you get 2 subsets, with the other feature we get 3 subsets. So whatever maths we come up with should address this particular challenge. All right, now another challenge could be that a feature splits into 2 subsets. One subset is pure and the other is not pure. Okay, so in that case, how do you measure the quality of the split? That is one challenge. A third challenge could be, so let's say it's a peculiar case, but it happens. So imagine a situation where we split on a feature, and what it did is, in one subset it only put one instance. Okay, so imagine there are, let's say in a group there are 10 examples. When I split it into 2 groups, it created in the first group there is only 1 instance, and in the other group there are 9 instances. That's how it split. So if there is a single data in a subset, it will be pure by definition, because there is only one class there. Okay, if a subset has exactly 1 instance, it is pure by definition. There is no impurity. But would you prefer such a kind of a split, where it only puts one customer into a group and retains everything else in the other group? Okay, so this particular split where it puts just one instance in one group, making it completely pure by definition, and everything else in the other group, which will almost retain the entire impurity of the parent. Okay, that compared against let's say another split which actually creates two groups, both of which are impure, let's say. Then which split is better? How do we compare them? All right. A fourth challenge is it's a natural one. Till now we have seen categorical features. That is easy to split. We only have fixed levels and we can only split on those levels. What if we have continuous features like age or income? Right? Age or income can take any value. So how do we split on continuous variables? Do we take all possible values? That's obviously not practical, right? It's continuous. We cannot split on every single value. So how do we deal with continuous values when it comes to splitting? So at this point, we know that we want some formula to measure the purity or impurity for that matter. Now in thermodynamics, we have a concept called as entropy, which is a measure of disorderness. Okay. In information theory, we also define entropy as measure of uncertainty in variables outcomes. Okay. Mathematically, entropy is defined as h of x, capital X is the random variable. H of x, entropy, is equal to sum of minus pi log pi. Where x is the random variable and pi is the probability of the ith outcome. So our random variable, it could be anything. So random variable is x and it has different outcomes. Every outcome has an associated probability pi. So we define entropy as sum of minus pi times log pi. So it's just the probabilities across the outcomes and we aggregate in this fashion, minus pi times log pi. Okay, across all outcomes. That's the entropy. Now in our case, the example that we have been discussing so far, the variable is default, okay, which has a Bernoulli distribution. So we are trying to predict a binary variable y, which is default or no default. That's a Bernoulli, that follows Bernoulli distribution, and it has two outcomes, one or zero, and the associated probabilities are p, 1 minus p. Okay, so if we want to calculate entropy, in our case it will be h of d. So d is the random variable default, capital D, which takes value 1 and 0, and p and 1 minus p are the associated probabilities to those outcomes. So entropy would be h of d is equal to minus p log p minus 1 minus p log 1 minus p. Just follow this particular formula. Okay, this is the original definition of entropy. Now one small note here. So we originally defined entropy as sum of minus p log p, where p is the probability of each outcome. For a two-class problem, which is what we are dealing with so far, this formula is symmetric. If you look at this formula, it is symmetric in the sense that if you replace p by 1 minus p, you get the exact same structure. It does not change. Try to replace p with 1 minus p, it remains the exact same. Okay, this is the characteristic of a two-class problem. When your random variable has two outcomes. When we have multi-class problem, so our y potentially would have more than two levels that we want to predict. That will be a multi-class problem. In that case, just use this formula. Okay, if let's say there are three outcomes, then there will be three associated probabilities. Accordingly, you can calculate the entropy. For most of our examples, we would deal with binary classification problems. So pretty much every time we'll use this formula. Now, how does this formula actually help? So before we understand the intuition behind this formula, let's talk about a few couple of caveats. okay, that we need to remember in these calculations. Number one is that this log that we have written here, it has a base of 2, not 10, not e, it has a base of 2. So it's log p base 2. All right. And the second caveat is, if p is 0, if the associated probability is 0, then we get an expression 0 times log of 0. Now we know log of 0 is minus infinity, so it becomes undefined mathematically, 0 times minus infinity. But we will treat this as 0. Okay, so when you are implementing this particular function in Excel or Python or anywhere, ensure that you address the this particular error scenario. Whenever p is 0, 0 times anything is 0, we are using that convention here. All right. Okay, so now let's get insight into how this formula actually helps to measure impurity. Okay, so consider a segment which has, let's say, 5 defaulted customers and 5 non-defaulted customers. Now we know that this is a completely impure segment. Okay, what's the probability of default in this group? It's 1 by 2. So 5 default divided by 10 total counts, that's 1 by 2. Now let's calculate entropy. Okay, now going by the formula, entropy is minus half log half minus again half log half, right? Because p is half and 1 minus p is also half, so we get minus half log half minus half log half, that is minus log half, which is 1. All right, so this segment has got an entropy of 1. Similarly, consider another segment which has 10 defaulted customers and 0 non-defaulting customers. What's the probability of default in this group? Probability of default is 1, because there are 10 customers, everybody defaulted, so probability of default is 1. Is this an impure segment or a pure segment? It's a completely pure segment. Okay, everybody defaulted in that group. Okay, so there is no shadow of doubt what happens in this group, everybody knows. Okay, so this is a pure subset and we get a probability of 1. What is the entropy? Use the formula. Entropy is equal to minus 1 log 1 minus 0 log 0. 0 comes because 1 minus 1 is 0. Remember the caveat, right? 0 log 0, we would treat this as 0. So we get log 1 is 0, right? And 0 times anything is 0. So 0 minus 0 equal to 0. So we get the entropy as 0. Okay. And let's consider the another pure segment, the opposite extreme, right? So in this segment, nobody defaulted, 0 defaults, and there are 10 non-defaulting customers. So this is also a pure subset, but in the completely opposite direction. What is the probability of default here? It's 0 because nobody defaulted. What's the entropy? Entropy is minus 0 log 0 minus 1 log 1. Again, that turns out to be 0. Okay, so now you can see how the formula works. We said that entropy measures impurity. So what we saw here is that for pure segments, entropy is 0, and that is the minimum. The lowest value of entropy is 0, and you'll get 0 only when the segment is completely pure. And for perfectly impure segments, which is our first case here, that's a completely or perfectly impure segment, entropy goes to 1. Okay, and that's highest. So entropy takes a value between 0 to 1. For pure subsets, you'll get a value of 0. For completely impure segments, you'll get a value of 1, and then you get everything in between, right? Depending on whether it's purer, then you'll get value close to 0. If it is like close to being perfectly impure, then you get a higher value. All right. So if we plot entropy as a function of probability, then we get a nice symmetric inverted U shape like this. I highly encourage you to try to plot this function in Excel. So this function entropy is a function of one variable. In this particular example, it is P. P governs the value of entropy. Try to vary the value of P from 0 to 1 because it's a probability, so it will take values from 0 to 1 and see how the entropy behaves. Okay, so as we discussed, entropy measures impurity, right? So as probabilities take values 0 or 1, those represent pure subsets. Okay, and at those value subsets we have entropy equal to 0, which is at the minimum. 0 entropy means perfectly pure subsets. Okay, and exactly at the middle, when probability is half, then we have a completely uniform mix of both classes, and that corresponds to a perfectly impure segment, and entropy is highest at 1. And in between we get all possible values between 0 to 1. Okay, so in this example you can see there are various examples that I've given for different subsets with different kinds of compositions. So there are two classes. One is denoted as plus, the other class is denoted as minus, and based on the composition of plus and minus in each group, you have P plus. P plus means probability of being plus in that particular group. So for example, in this case, P plus is 2 by 10 because there are 2 plus out of 10 examples. So as and when the subsets become purer, see, this is a pure subset, all minus, this is another pure subset, all plus. In either of these subsets, because they are both pure, the entropy is minimum at 0. And this is a perfectly impure subset, so we have entropy equal to 1. Now let's do a sample calculation for an intermediate value. So let's say calculate entropy at P equal to 0.7. So we use this formula, minus 0.7 log 0.7 minus 1 minus 0.7 will be 0.3, so minus 0.3 log 0.3, that comes out as 0.88. Now this 0.88 is close to 1, right? Remember, 1 means completely impure. So 0.88 is close to 1. The reason is probability is 0.7. 0.7 means it is close to 0.5. And 0.5 means, P equal to 0.5 means it's a completely impure segment. So that's why we get a high value of entropy, meaning it is it has high impurity. All right. Okay. Now that we have a mathematical model of impurity, which is entropy, how can we actually use this to split on the most informative attribute? So let's say that we have a parent set which has n instances, and we are contemplating on splitting on a particular feature. We haven't split it yet. We are trying to decide which feature to split on. Okay. If we split on a feature, it will result in, let's say, 2 subsets. Okay, we have parent which has n instances, then we'll get 2 children, child 1 and child 2, which will have, let's say, n1 and n2 instances respectively. Okay. Now, obviously n1 plus n2 is equal to n. How do we actually use the entropy measure to evaluate the quality of this split? All right. The idea is very simple. Children must be purer than the parent. Okay. Otherwise, there is no point of splitting. Now, with this split, we expect that the combined entropy of the children sets to be lower than the parent. And in other words, we are actually looking for the reduction in entropy. Okay. Parent had some entropy, so we can calculate entropy given a subset. If we have the composition data of the class representation, then using the entropy formula, we can calculate the entropy of a particular group. We can calculate the entropy of the parent. We can calculate the entropy of the children. how much purer are children compared to the parent. That will determine the quality of the split. So to measure that, we need to find out the reduction in entropy. Okay, this reduction in entropy has a name. It's called as information gain, and this name is very natural if you ask me, because what we want to do is get more and more purer subsets. Okay, when we are in an impure subset, we are actually not informed about the class of a particular example. But once we land in a purer subset, we have much more information about the nature or the characteristic of a particular instance in that class, right? So with the help of splitting, when we are reducing entropy, we are reducing impurity, and the subsets are becoming more and more purer. In other words, we are getting more and more informed in terms of what kind of group that would that be, okay, with respect to a particular class. So we are getting information. So this is called as information gain. And information gain tells us how much information we have gained about the target variable that we are trying to predict with this particular split. Okay, but we need to do one adjustment to this particular formula to make it correct. So when we say combined entropy of the children, it is not the blunt summation of individual entropies of each child. No. We also need to account for how many instances goes to a child subset, right? It's obvious. For example, consider this. So let's say we had 50-50 default and non-default to start with, and then on a given feature, we're not worried about what feature it is, but after we split, it created two children subsets. In one of the subsets, there is only one instance, one default, okay, and in the other group, it pretty much kept everything else. So except one, everything else got dumped into the other subset. Now, do you qualify this as a good split? It's not, right? First of all, we should not have one instance in any particular subset that leads to overfitting. Okay, if I create a branch like this and there is only one default, what is the probability of default in this subset? It's 100%. So any customer who falls in this group has a 100% chance of defaulting. That's not practical at all. And if I measure the quality of the split by simply adding the entropy of this plus this as the total combined entropy of the children, then that is not accurate, because although this is pure, there is only one instance. This is a pure subset, but there aren't many people for me to be confident about the characteristics of this particular segment. Okay, this is a big segment. There are a lot of people in this group. So the representation from a total instances perspective is high, but it is impure. Okay, so that's the problem with this group. So what I'm trying to say is, when we're trying to find the total combined entropy of the children, do not do a pure sum. What's the alternate? We have to do a weighted sum. Weighted sum would be the right way to go about it, because it's not enough to say, okay, this is pure, that is impure. It also matters how many are pure in that group. Okay, so that also matters. So when I am trying to find out information gain or reduction in entropy, the formula that I will use is this. So entropy, information gain Ig is equal to entropy of the parent minus, it will be the combined entropy of the children, but we have to take a weighted sum. So entropy of child 1 weighted by the weight of child 1, so that's just n1 divided by n1 plus n2, and then entropy of child 2 times the weight. Weight would be n2 by n1 plus n2. So always remember this when you're trying to find combined entropy. You have to take the weighted sum, because it is not enough to just say that this group is pure, this group is impure. It matters how many instances are there, because if there are a lot of instances in a particular, if there is a split which is pure and there is a huge population in that group, then that gives you a lot of information. Okay, this group must be this kind of people live in that particular group. Okay, it tells you a lot about the characteristics of the people who are part of that group, if there is an overwhelming population in that. But if there is just one or two instances, then it's really not. The sample is too small for us to be confident with our prediction. Okay, so whenever we take measure information gain, it has to be parent minus weighted sum of entropies of the children. Okay, and we want to do a split that maximizes information gain, or maximizes the reduction in entropy or impurity. Okay, let's take an example and go through the calculations. So let's say there are 30 instances in the parent node. Okay, and there are two classes. It's denoted as star or dot. So you can see there are 14 star instances and 16 blue instances. It could be anything. Okay, now if we calculate the entropy of the parent, it will be simply use the formula. So we have probability of dot as 0.53. We can use that, or we can use the other. Remember, it is symmetric, right? So you can, it's the whole formula is symmetric. You can take any probability and put it in the formula. You'll get the same answer. So we get 0.99. Okay, we get 0.99 as the entropy of the parent, which indicates that it's a very, very impure subset. And that is true, because there is almost equal representation of both classes. Okay, now we split it into two children. So child 1 has 13 instances, 12 dot and 1 star, and the branch that is created is using this rule, balance less than 50k. All right, and we get the entropy of the first subset as 0.39. Similarly, on the other side, we have we get 17 instances on this particular subset, 13 stars and 4 dots, and the entropy is given as 0.79. How do we calculate the quality of the split, or the reduction in impurity or information gain? How do we calculate that? Information gain is equal to 0.99, that is the entropy of the parent, minus entropy of the child 0.39 weighted by its weight. Its weight will be 13, 12 plus 1, 13 divided by 30. Similarly, for child 2, the weight will be 17 by 30 and multiplied by the its entropy. Okay, so that gives us 0.37. 0.37 is the information gain or reduction in entropy if we decide to split balance at 50k. All right, this is the quality of this particular split. Right now we are contemplating. There are many features available, and per feature there are also many values. So if it is a categorical variable, then obviously we can only split on the fixed levels that are there. But if it is a continuous variable like balance, we can split it at many different points. We can split it at 50k, we can split it at 20k. So that also becomes part of the algorithm. The algorithm tries to find the feature and the value at which it will split, so that the reduction in entropy is maximum, or the information gain is maximum. All right. Please pause the video at this point and go through all these calculations on the slide yourself to make yourself comfortable. Okay. So now we are going to split the same data on another feature, which is residence. Okay, so we got the same parent, 30 instances. This is the distribution. But now we are splitting on another feature called residence, which is obviously a categorical feature. There are three levels: own, rent, or other. We are doing a three-way split here, and we can calculate the reduction in entropy in this case as well. It's the same thing. You just use weighted sum while calculating the combined entropy of the children. So we know the entropy of the parent is 0.99, and I want you to calculate the entropy of the three subset that we created. Okay, 0.54, 0.97, and 0.98, and then the reduction in entropy or the information gain would be 0.13 from this particular split. Please try this out to get familiar with all the calculations. Okay, now question is, which split is better? So we split on balance, and now we split on residence. When we split on balance, we got the information gain as 0.37. Now we are getting information gain as 0.13. Remember, information gain is reduction in entropy. Entropy is impurity. So more the reduction, better the split. All right, more the information gain, better the split. So reduction in entropy or impurity was higher when we split on balance. It was 0.37 there. So that means this, if you put it in a decision tree algorithm, it will at this particular stage, it will choose to split on balance, not residence. Okay. And also note that in splitting residence, the category category own has reduced the entropy significantly. Okay, it's now 0.54. Initially it was 0.99, the entropy of the parent. The entropy of this particular child is pretty good. You can see there is only one star and a lot of dots. So this group primarily is dot. Okay, so it's almost pure. But if you look at the two other children, they retain the impurity of the parent almost. It's 0.97 for this child, 0.98 for this child. So they pretty much retain all of the impurity of the parent. So we understood that information gain is the silver bullet to all the four different challenges that we discussed regarding supervised segmentation, right? It's the one mathematical measure that we found which takes care of all these different challenges that we had. Now with this help of information gain only, we can get the optimal split, right? So that's pretty cool. Now, can we use supervised segmentation for a regression problem? Is that possible? That means now our y is a continuous variable. Answer is yes, we can. Only thing is that we cannot use information gain, right? So how can we tweak that formula to make it suitable for regression? See, information gain was information gain measured reduction in entropy or reduction in impurity, correct? What's the measure of impurity for a continuous variable? Answer is variance. So if we split the node on a feature that gives the maximum reduction in variance of y, then we can make that as part of a regression algorithm. Okay, this will result in children having low variance, right, or children having more homogeneous y compared to the parent. What is variance? Variance means how much y is varying around the mean. Okay, if y is constant, then in a particular group, if y is, let's say y is constant, y equal to 5, anybody who falls in that group, I can predict y equal to 5. If there is a whole lot of variance in that group, then I cannot really predict y. Okay, so in the parent there could be all possible y's. That's my original regression problem. There are a bunch of x's and there is y. In the parent data or the original data, there will be all kinds of y's. So blindly, if I want to predict y, if I take average y of everything and give the prediction, that will be a blunt prediction. But I can do better. With the help of features, I will start splitting and creating more homogeneous groups. Homogeneous groups in this case would mean the y of various examples in a particular group will be close to each other. So let's say we get a group where the y's are 5.1, 4.9, 5.01, 5.2. That means anybody who falls in that group, I can say your prediction of y is 5. That's the whole idea. Now, how do I ensure that I create groups where y is not varying so much? By reducing variance, right? So for continuous problems or regression problem, I can replace information gain with variance. Variance becomes my measure of impurity. Okay, everything else remains the same. So note that here in this case, I'll take the variance of the parent, then combined variance of the children, and I will find the reduction in variance. And the formula that I will use, I obviously have to ensure that when I'm taking the combined variance of the children, it has to be a weighted sum. Okay, do not blindly add the variances as is. We have to take the weighted sum. That's all. So we talked extensively on how a single split will be performed, right? Once we do a split, we can treat the children as the new parent and split the children using the exact same procedure and get grandchildren, right? With every successive split, we will be reducing entropy further and further and getting purer and purer subsets. In this process, we will end up building a tree, which is called as a decision tree. All right. So let's familiarize with some tree nomenclature with the help of an example. So let's say our original data set had 50 default and 50 no default cases. This is the root node. Okay. Then with the help of information gain, we decided to split on the feature balance. Balance is a continuous feature. We can split at any value we want, right? Let's say the optimizer figured out that if we split at 40K, then we get the maximum information gain. Okay, so that's our first split. Now we got two branches, one with my balance less than 40K and another as greater than equal to 40K. So these are called branches of the tree. And we got two children nodes. These are called as decision nodes. Okay, and we continue the process. Just treat every child as a new parent and continue the same infrastructure to get purer and purer subsets. Okay, and you can, if it is a continuous feature, it can be split again and again. Okay, but if it's a categorical feature, then you can potentially exhaust all the levels and you cannot split on the same feature again. All right. So for example, if you look here, rent equal to own, you are on this on this particular subset, and let's say there are only two levels available: rent equal to own and rent equal to other. Once you are in this subset, any other subset that you create out of this, everybody has rent own. Okay, there is no mix of rent equal to own and rent equal to other in this group anymore. So you cannot split this in on rent feature anymore. Same with this also. Okay, but if you split on balance, balance can be split on any value. So once we are in this less than 20K zone, you can further split it into, let's say, less than 10, greater than 10. Okay, so that's one of the differences. Now finally, when we decide to stop, we land at leaf nodes. This is so that's why it is called as a tree. We start with the root node, and then we create branches. These are the intermediate nodes called as decision nodes, all the way up to the leaves of the trees. Okay, these are called the leaf nodes. And basically you can visualize a tree upside down. Okay, the root is supposed to be at the bottom and leaves should be at the top, right? And this is a tree completely upside down. That's it. So these are some of the key terms that you need to know from a decision tree nomenclature perspective. Once we reach our leaf nodes, our tree is complete. Now let's label the final nodes or segments we got. So the first one is simply whoever has balance less than 20K. That's the definition of this segment. The PD in this segment would be 40 divided by 45. That's the probability of default in this group. All right. The second segment, we can say the balance would be between 20K and 40K. Okay, because if you look at the branching, so you have to follow the branching starting from the root all the way up to that particular leaf node. So if you see, initial split was balance less than 40K. This zone, this particular group has balance less than 40K, all of them. On top of that, again, this is balance greater than equal to 20K. That means the resulting group will have balance greater than equal to 20K and less than 40K. So it's between 20K to 40K. Okay, that's the definition of this group. And the PD of this segment is 5 divided by 25. Similarly, the third segment is balance greater than 40K and rent equal to own. Okay, and the PD of this segment is 2 by 22. And the final segment has a definition of balance is greater than equal to 40K and rent is equal to other, and this node has a PD of 3 by 8. Now, how to predict the probability of default of a new customer? It's easy peasy, right? Find out which segment the customer belongs to based on his balance and rent status. Any customer would be part of one of these four groups. Okay, so based on whichever group he belongs, that person will inherit the PD associated with that particular group. Okay, so if a person falls here, then the probability of default of that person would be 5 by 25. Decision tree is in credit risk industry. Decision tree is the most popular algorithm still in use for mostly for retail pool segmentation purpose. Okay, so we use logistic regression, that is also massively popular, and the next in line is decision tree. Both are very popular in credit risk industry. How to carry out regression using decision tree? So we briefly spoke about it, right? So let's say instead of PD, we want to predict the FICO score, which is continuous. FICO score is a continuous variable. It can take any value. I mean, decimal values are not allowed, but it has a whole range of values, right? So only two things are different. The splitting scheme depends on the largest reduction of variance, right? So that's what we already talked about. And so what we need to do is y is continuous, so we will keep a track of the average y and the variance of y in every node. Okay, when we split, we want to calculate for every node we'll do this. For every node we'll calculate the average y in that group and the variance of y. When we do a split, we can calculate the average y of the groups and the individual variances of the two groups. Now, how would we know at what point to split? Well, the combined variance of the children should be as low as possible, right? So we'll seek for that particular split that results in maximum reduction of variance. Okay, so once we identify the split that reduces the combined variance, we will go ahead with that split and we'll record the average y of that particular node. I'll tell you why we use average y. And then we'll keep doing that, right? We'll keep continuing until we reach the leaf nodes. Okay. So the first thing that we did differently is instead of information gain, obviously we cannot use that here. We are using variance to reduce impurity. Okay. Once we reach the leaf nodes, my final prediction of y is the average y of that group. Straightforward, right? So when we reach the leaf node, for example, here in this case, the prediction of FICO score in this group would be the average of FICO scores of all customers part of this group. Okay, for balance less than 20K, if we want to predict a continuous variable, instead of, when in case of PD we calculate the proportion, right? But in case of predicting a continuous variable, we'll take the average y in that group. So that's all there is. Okay, so this is how you can tweak the decision tree to address a regression problem. Okay. The algorithm that we discussed so far is essentially a divide and conquer algorithm. The way we approach this problem is that we have a parent set of, the original data set, and we are not very sure. So what we do, let's divide it and become more informed. Then again we divide it. So at every stage we are dividing and conquering. So it's a divide and conquer theme going here. It's a recursive partitioning technique, right? Where we are dividing the data to make the children purer and purer than the parent. However, this algorithm suffers from a flaw. You see, when we split, we only care about the parent and the immediate children. We don't care about the grandchildren at that point, right? So what we are relying on is actually a greedy algorithm. It only cares about the current split, not the future splits, right? It's greedy because it only cares about the immediate benefits or immediate future, short-term future. It doesn't care about what happens after 2 or 3 splits. Are those optimal if I take this route? It doesn't care about that, right? That's why it's the greedy algorithm. Now, greedy algorithm may not result in a globally optimal tree. Okay. So is there a way to build a tree that is globally optimal? Nobody knows. We don't know. In practice, we still use this greedy algorithm. Okay. So in the past, we have explored several classification algorithms, right? Logistic regression, support vector machines, linear discriminant analysis. In all of those, there was a common theme going on. The common theme was we used to derive a mathematical function that would serve as the decision boundary, right? By minimizing some loss function. We used to derive that decision boundary, and anything so once we have a decision boundary, then points which are to the left of the decision boundary would be classified into one class, and points which are on the right side, it could be left, right, or above, below, depends, I mean, how you see it. So that was the main theme, right? In all these algorithms previously, we always had a mathematical function to serve as the decision boundary. Okay. Now, when the data looks more or less separable like this, we use these standard classifiers such as logistic regression or SVM, LDA, which are basically functions of the features. A mathematical function of the features could be linear, could be non-linear. Right? Accordingly, you get a linear decision boundary or non-linear decision boundary, and then that helps us to classify different points into different classes. And decision boundary is a mathematical function. But what if the data looks something like this? Right? A single boundary in form of a mathematical function will not work. Okay, there are data points which are in form of clusters. They belong to discrete zones, if you will. Okay, so we need to break this space into zones by horizontal and vertical lines. All right, this is exactly what decision tree does. Decision tree does not use any mathematical functions. It simply divides and conquers, right? So if you look at decision tree algorithm, at every step we are creating branches by branches based on a particular feature. Okay, by splitting on a particular feature. When you split on a given feature, it's one feature at a time. We are not combining features. When we do a split, we are not doing balance plus age. That is not happening here, right? It's always one feature and a given value. When you use that particular splitting scheme, essentially you are creating horizontal vertical decision boundaries. Okay, because you're not combining features. It will be parallel to a particular, or perpendicular to a particular feature, x1 or x2. So you can see in this example, right? So this is what the decision tree does. There is no mathematical function. It simply divides the zone using horizontal vertical lines with one single feature at a time. Okay. In this example, if you see, there are three leaf nodes, 1, 2, 3. Node 1 is this is node 1. This is x1 less than equal to 10 zone, right? So we split the parent by this, x1 less than equal to 10 and x1 greater than 10. That resulted in, so let's say we stopped splitting after this. So this is a leaf node. Now this leaf node 1 is characterized by this zone, x1 less than equal to 10. So if I show you the plot, 1 belongs here, x1 less than equal to 10. So it created a vertical boundary at x1 equal to 10, and the left side of this is zone 1. That's what decision tree did. Okay, so this is to give you a visual understanding of what the tree is doing in terms of creating decision boundaries. All right, similarly, if you look at x2, it's the zone where the number 2 group, right? x1 must be greater than 10, x2 must be less than equal to 12. So this group, x1 must be greater than 10 and x2 must be less than 12. Again, this one is zone 3. All right, so there are two key differences that you have to remember. So this is in contrast to the other algorithms, what it is actually doing. Number one, there is no mathematical function in terms of combining features in an intelligent way to learn some kind of function. That is not happening. Okay, in all other algorithms you will see a blend, features coming together in linear or non-linear fashion, and through a mathematical function which essentially becomes a decision boundary, I am able to classify different instances. Here there is no mathematical function like that. Okay, and the other salient feature of decision tree is the decision boundaries are horizontal and vertical. In two-dimensional plot it looks horizontal vertical. In higher dimension it will be just parallel to different features or planes. Okay, there will be no angles, like other than 0, 180 degree. You can think in those terms, right? So that's the other feature of decision tree. What will happen if we keep splitting? Well, eventually, when we keep splitting, we'll end up with exactly one instance in each of the leaf nodes, right? If we do that, it's called as a full tree. So basically, tree is grown to the fullest extent. Now, do we really want a full tree in practice? Answer is no. We talked about this multiple times. Why? Because we want to avoid overfitting, right? We want to retain some impurity in the leaf nodes to generalize things, right? Um, so that's what we discussed before. So we need to stop splitting in between somewhere, and the criteria to stop could be enforced in variety of ways. Okay, so these are called as stopping criteria. So here are some examples. We can stop at maximum depth. So let's say we split. So depth basically means the distance from the parent to the lowest layer wherever you are. Okay, so for example, if you look at the first split, if we want to stop after first split, then we are basically stopping at depth equal to 1. Okay, similarly we can provide a maximum depth equal to 2, so it will do another split max, but it will not go beyond that. So it will split this node, it will split this node, but then that's it if the maximum depth is given as 2. So we can control the growth of a full tree by enforcing some of these stopping criteria. One is maximum depth, the another one is minimum sample split. That means if the number of instances in a particular subset is going below a threshold, then we'll stop. We want to ensure there are minimum, let's say 5 samples present in all the groups. We don't want to go into a situation where there is very few instances left in a particular subset. That's not a good idea, right? So we want to ensure there is some sizable population left in each of the leaf nodes. So minimum sample split. We can also specify minimum impurity decrease. So in every split, what we are trying to do, we are trying to reduce impurity, right? If the reduction in impurity is minimal, so let's say from 0.5, right? The reduction, so if you take the difference in impurity, let's say it's 0.001, it's not really worth it, right? I mean, that impurity reduction is practically insignificant. I can probably avoid that and have, avoid overfitting as well. Okay, I'll get a minor improvement in accuracy, but if I stop the splitting, I'll avoid overfitting, right? The more you split, you're moving more towards overfitting the tree. Okay, so there are many different hyperparameters that we can use to enforce early stopping, basically. Okay, so we will see an end-to-end implementation in Python, both for classification use case as well as regression use case. Then I'll walk you through the entire set of hyperparameters available in scikit-learn that we can control or play with to design the tree that we want. Okay, yeah, so these are called as stopping criteria. Now there is another way to avoid a full-grown tree. The idea is to first grow the tree fully, okay, and then remove the sections of the trees to avoid overfitting. Okay, so it's like first grow the tree to the full and then chop sections of it. All right, this approach is called as pruning, and it achieves the same result, right? The underlying goal is to avoid overfitting, but it's little complicated, but we will cover this in the later section. Okay, so continuing with the idea of stopping criteria, which is primarily used to avoid overfitting, we sometimes used a smoothed version of probability estimate is called as Laplace correction. So let's consider a node with n defaulted customers and m non-defaulted customers, right? The PD of the segment as per frequency based approach is simply n divided by n plus m. Now this formula gives us a very skewed estimate, right, when the number of instances are small, and we know that. It's very simple. So let's say there is a coin toss experiment and you toss the coin 2 times. Both times it came as head. Going by frequency based approach, you would say the probability of head is 100%. In small samples, there is always this um, frequency based approaches do not give a good number. All right. So to avoid that, we instead use a smoothed version of this raw frequency based estimate called as Laplace correction. And the correction is very simple actually. It just dilutes the effect of skewed probabilities, which is a consequence of small samples. How does it do that? This is the modified version of the probability. It's n plus 1 divided by n plus m plus 2. Okay, and this will dilute the effect of, or it will smooth out these extreme probabilities. Okay, so yeah, this formula still pretty much is close to this raw estimate if n and m are large. Only if there is a small sample problem, then the smoothed version or the adjusted PD using Laplace correction gives us a better, a more usable practical estimate. Okay, so we'll see an example. For example, consider this segment. So here there are ample number of class representations from both sides. There are 20 defaults and 10 non-defaults. The probability of default using frequency based approach would be 20 divided by 30. And if we use Laplace correction, it will be 21 divided by 32, which is pretty close to 20 by 30. There is not any radical difference between these two estimates. But now consider a small sample, something like this. So there is one defaulting instance in the entire group. There is no default. So going by the frequency based approach, it will be PD equal to 1, right? Because it's a pure subset with one single instance. We want pure subsets, almost pure subsets with a sizable group. That's what we want practically. Okay, so this is pure, but it has only one instance. We totally need to avoid that. But if this happens, still the Laplace correction will come to rescue. So if you use Laplace correction, the probability is 2 by 3, and that's not too bad. Okay, this estimate can work. It kind of gives a little Bayesian flavor, right, in terms of not using the data as is and inducing some kind of adjustment, but yeah, it will dilute any such skewed probabilities that might come up if the sample size is not adequate. Okay, so 2 by 3 is more sensible than 1. I can use 2 by 3 in practice. Okay, so just like the entropy measure, which is a measure for impurity, we have another measure called as Gini index, which is also very popular, that also measures impurity and is given as 1 minus sum of pi square. And we know what pi is. Pi is the probability associated with ith outcome. Okay, so we take all such probabilities with across different outcomes and square them, add them, and then 1 minus of that will give you the Gini index or Gini coefficient. So like entropy, Gini also has the inverted U shape. Okay, but it takes values between 0 and 0.5. Remember, entropy takes value between 0 and 1, but Gini index takes values from 0 to 0.5. And if the it behaves similar to the entropy. So you see the shape is similar, and when the subset is pure, so probability is either 0 or 1, then Gini index is 0. Okay, so you just put pi is equal to 0. So let's say, so okay, if probability associated with one class is 0 and the other class would be 1. Okay, so sum of 0 square plus 1 square is 1, 1 minus 1 is 0. Similarly, if you put pi equal to 1 and the other one would be 0, it will be 1 square plus 0 square, again 1, 1 minus 1 equals 0. In either case, if it is a pure subset, Gini coefficient will be 0. That's what you see here and here. And if it is impure, then Gini coefficient becomes 0.5. So you know what pure, so let me use this word, purely impure. Okay, purely impure means probability would be half-half. So in that case, this particular sum would be 1 by 2 square plus 1 by 2 square, which is 1 by 4 plus 1 by 4, which is 1 by 2. So 1 minus 1 by 2 is half. That's what we see here. Okay. Here is one exercise for you. Show that for a two-class classification problem, Gini is given by this expression. Yeah, just try it out. It's easy, it's straightforward. Now, some of the popular algorithms that are used as part of building decision trees are as follows. The first in line is CHAID or CAID. You can call whatever you want. It stands for Chi-squared Automatic Interaction Detection, which was introduced in 1980, which is still used in industry in credit risk domain. So basically it uses chi-square test of independence of groups as a splitting criteria, right? So when you are splitting, the two groups should be as independent as possible. So based on chi-square statistic, you decide the splitting criteria. Then we have CART. CART stands for Classification and Regression Trees. This came in 1984 and is extremely popular. You'll find CART in most of the software packages. In fact, in Python scikit-learn, it actually uses CART algorithm. And we have some other packages such as C4.5 and C5.0, which are also very popular these days. So in the next video, we will see a couple of implementations useful in credit risk domain in Python using scikit-learn library. One for classification, which is so basically we'll take a probability of default example with the real data, and we'll do one regression example. So in credit risk domain, probably one of the candidates for regression is LGD. So using decision tree, we will implement a regression algorithm to find out LGD. And here is the scikit-learn documentation. So I would recommend that you go through this documentation to learn more about the implementation details. We'll do an end-to-end example, but there are a lot of good information in this particular URL. So as I mentioned, scikit-learn uses the CART algorithm. So that's what we will see. All right, see you in next video. That's all for now. This is Satya from Peaks to Tails. Thanks for watching.